want to make sure that
Sweet. So
I just want to make sure people can hear me and understand me.
Kareem, can you confirm that you're hearing us by doing this, maybe?
Yeah.
Thank you, Kareem.
Thank you. And we have Lean now joining. Lean, if you can open your camera, please do. And everybody, like maybe this time because we didn't tell you.
I'll open my camera, just give me a minute.
Thank you, Lean. Thank you. This time we didn't tell you, but next time, please be ready to open your camera. I think it's very important. So welcome, everybody. I want to introduce you to really, really good people, John and Mark, Dr. John and Dr. Mark. They are from the Irish team of the Math Olympiad. They are helping us at the moment to up-level our skills in as students. So you guys want to compete at the IMO, right? So they want to help you accomplish, like make a better performance at the IMO. So that's why they are here. Please feel free to ask them questions, treat them with respect. You know the drill. This is not your first training. So Mark, I will leave the mic to you. I'll be here if you need me. But it's all you now. Good luck.
Okay, thank you. Thank you. I'm going to see if I can set this up to write, and so you can see everything. So first of all, salam alaikum to everybody, and I'm very happy to try and get this started. If you can just feel free, by the way, to talk. You can turn off your mic and ask me questions at any time. I'm very happy to hear questions. And it's nice to hear you speak, because then I know that you can hear me and we can communicate. So that's the first thing. I'm going to try to share content with you now. So I'm going to try and share my screen. And hopefully this will work. So can you tell me, can you see the icons on my screen?
Yes, we can.
You can see them. Great. Thank you. Thanks for confirming. So I'm going to set up somewhere where I can actually write, and I want to see that you can actually see what's written here. I'm just going to try writing. Can you see my writing appearing on the board?
Yes, we can.
Yeah, great. So this is going to be our classroom, our blackboard, and I'm going to try to discuss mathematics with you now. We had a conversation many weeks ago about topics that you guys were interested in, and the topic that many of you asked me to talk about was the topic of complex numbers. So I'm just going to write this here, and I'm going to give a little presentation for the next maybe 45 minutes or so on complex numbers. Now, I want to say a few things first. I don't know how much mathematics you guys know, so perhaps what I talk about here will seem very basic, very easy for you. And I'm sorry if that's the case, but I think it's good to start with something basic, mostly because I want to make sure that technology works, that we can communicate with each other. And then if you want to ask me questions along the way, please ask me questions. I love questions. I love hearing your voices. So ask anytime, interrupt me, ask me questions. That's great. And you can then tell me at the end if I'm covering things you already know really well and you want to get to more advanced material. That's fine. We will. I mean, we will get to more advanced material, but I want to start by talking about complex numbers, try to give you some interesting discussion on this subject, and maybe some little problems to solve. And this will help strengthen your background understanding for Olympiad problems. So first of all, is that a reasonable thing to do? Great. Okay. So I'm going to start just discussing a little bit about what complex numbers are and the history of complex numbers. And as I said, feel free to interrupt me at any point. Okay. So I want to start by mentioning two problems. Okay. So two mathematical problems, two math problems. So the first problem concerns solving equations. So solving equations. Is everybody able to read this and can hear me? Yes? Great. So, okay, so let's consider a very basic example. You all are aware of quadratic equations, I know. So we have a quadratic equation which has the general form a times x squared plus b times x plus c equals 0. And we're assuming here that a is a non-zero number, right? Everyone happy with that? And we can actually, just to make life a little bit easier, let's assume that a is positive. If I assume that a is positive, then I know that this function has a nice graph. So the graph of the function will look something like this. Or it might look something like this. Or it might look something like this. Okay. So this is the case when a is a positive number. And you can see in these three cases, there's three important differences here. In the first case, you can see that the graph crosses the x-axis. So this is my x-axis. This is my y-axis. You can see that the graph crosses the x-axis in two places. Here and here. You can see in the case, in this blue case, it touches the x-axis at one point, and in the green case, it never crosses the x-axis. Now, there's an algebraic interpretation of this. So there is a formula, so-called quadratic formula. And I think the first person to solve the quadratic equation fully was, of course, the Persian mathematician Al-Khwarizmi. I may not be pronouncing that correctly, so I'm sorry if I got that wrong. Al-Khwarizmi was in the House of Wisdom in Baghdad, as I'm sure you probably have all have heard. And the formula, he may not have written it in this way, but the formula effectively says that if I want to find x, x is given by minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. So all of you know this formula, I'm sure, okay? And you see that in this particular formula, we have this expression here inside the square root sign. And so we have sort of three possibilities. And the first possibility is that the b squared minus 4ac is a positive number. And that's, of course, the situation when the graph cuts the x-axis in two places. And we get two possibilities here, the so-called roots of the polynomial, or the solutions to the equation. And the second possibility here is this blue one. This is the case when b squared minus 4ac is 0. And of course, the third possibility here, this is the case when b squared minus 4ac is a negative number. And this is the one that we're very interested in here, okay? So what is going on here? So now we have a situation where we're dealing with, in this particular case, the square root of b squared minus 4ac. And this number here is negative. Okay, so the question is, what is this? What do we do with this type of quantity? Okay, so I mean, just to look at a couple of examples. So we take the equation x squared plus 1 equals 0. And if we solve this, we see that x equals either plus or minus the square root of minus 1. So what is that? What do we mean by that? Okay. Take a maybe slightly more complicated expression, x squared plus x plus 1 equals 0. And if we solve this using the quadratic formula, we get that x equals minus 1 plus or minus the square root of 1 minus 4 divided by 2. And so when we tidy this up, this is minus 1/2 plus or minus 1/2 times the square root of minus 3. Again, what do we mean by this expression? What do we mean by this expression? Okay, so this is something that you know caused some some problems for mathematicians to try to understand, well, what do we do with this? What do we do with this expression? So before I go any further, is everybody able to hear me and understand me? And are there any questions so far?
Yeah.
You're happy? Yeah? Everyone happy? Okay. I just want to make sure you're happy and you understand. And please, if there's any question, just interrupt me, okay? The most important thing today is that we're all able to communicate and that the technology works. Okay. So am I correct in saying that everything I've said so far is something you already know? You've already seen this in school. This is familiar to you. Is that fair? Yeah, please tell me if it's not, or if there's anything you want me to clarify. Okay, great. Okay, so these are a couple of examples, right? So that the question is, what do we do with that? Let me consider a more general, a slightly more general type of equation. So what about so-called cubic equations? So these are equations that look like this. We now have an x cubed term. So we have ax cubed plus bx squared plus cx plus d equals 0. And again, I'll assume that here that the a term is not the number 0. Otherwise, this is no longer interesting, or well, no longer cubic. Okay. So now solving a cubic equation is harder. It's more difficult than solving a quadratic equation. There is a formula. Okay. So there is a cubic formula, just like you had a quadratic formula for the, if we go back up for the quadratic equation here, we have a formula like that. In the case of the cubic equation, the formula is much more complicated. And so I'm not going to bother writing it down today. If you're curious about the cubic, we can talk about it another time. I just want to mention that there is a formula. But it turns out when you're trying to solve the cubic equation, lots of terms of this type, the squares of negative number terms, appear. Okay. And so to give you an example, so I'll just write not today. We won't talk about the cubic formula today, right? Maybe some other day. But here's an example of a cubic equation. Let's take the equation x cubed minus 15x minus 4 equals 0. Okay. Now, I'm going to skip ahead. We want to solve this equation. I'm not going to go through deriving the cubic formula or anything like that. I'm just going to tell you that one of the solutions looks like this. So after some work, you can get a solution which looks like this. X equals, I worked this out earlier. This is the cube root of 2 plus the square root of minus 121 plus the cube root of 2 minus square root of, sorry, made a mistake, minus 121. Okay, so you get this rather complicated looking expression. Don't worry right now about how I computed that. I'm skipping those steps. But you notice inside here, we have a square root, we have a square root. By the way, just to be clear, this expression here, when I say cube root of 8, I mean 2, right? So this is just, this is the same as 8 to the power of 1/3, right? So something like this, you understand. This is straightforward enough. The problem, however, is when I start dealing with numbers like this, okay, or this. That's where we run into difficulty. Okay. All right. So you can see in general, not just quadratic equations, but solving equations more generally, these kinds of expressions, square roots of negative numbers, appear. And so this was a big problem. So one mathematician who was very much involved, if you want to look him up, in dealing with cubic equations, so was Cardano. And Cardano realized the importance of these square roots of negative numbers. okay, and was one of the first people to sort of really try to understand them and figure out how to use them in solving equations. Okay, so I'm going to come back to this. Okay, so we will return to this problem. Okay, any questions so far? I'm going to move on to a second motivational problem. Any questions from anybody so far? Nothing? Are you happy? Are you upset? No response.
Yes, we are happy.
What's that?
Yes, we are happy.
You're happy, okay.
Mm.
Thank you. Okay, I just want to make sure it's working, that you can actually understand me, you can see what I'm writing. I'll try to make it more interesting, okay? I'm gonna, I'll try and get better, but I just want to make sure you can follow me and understand me. I sometimes speak, I've been told I sometimes speak very quickly. So if I'm speaking too quickly or too fast, just tell me and I'll try to slow down. I'm sorry, I don't speak any Arabic, so we have to do this in English. I hope that's okay.
That's okay. I think so far so good.
Okay, great. Thank you. Thanks for telling me. Okay, so let me go back. Let me just go back to what I was writing. So I started with the first problem, right? The first problem is solving equations. And I explained to you that when you're solving equations, interesting numbers appear, numbers like this, square roots of negative numbers. And we want to try and understand what do we do with that. So that's one problem. Let me give you a second problem, which turns out to be closely related, but it's more geometric problem. Okay. So this is the second problem. Okay, it's the second problem. So I want to just talk a little bit about space and numbers and the way we think of numbers in terms of a space. So just to remind you, this is the notation we're going to use throughout. So this is what we call the natural numbers. And so on. All of the whole numbers, positive whole numbers, these are the natural numbers. Again, I'm sure you've seen all these things in school. We then have the so-called integers. These are the numbers that include the natural numbers, but we also have 0, and we have the negative numbers. Okay, the integers. And we'd also like to have fractions. So we have this set of numbers, which we write as a divided by b, such that the a and the b are integers. And we don't want the b to be 0, right? We don't want to be dividing by 0, so we add in this part here. And these are the so-called rational numbers. I'll just make this a little bigger. Hang on. Okay. And finally, well, not finally, but the next sort of collection you learn about are the real numbers. And all I'm going to do here, this is a bit complicated to define, so I'm just going to write down decimals. These are the so-called real numbers. So everybody, I'm sure, has seen this notation. Yes, you've all seen these descriptions. And you all know that these are subsets of each other in the following sense. The natural numbers is a subset of the integers, which in turn is a subset of the rational numbers, which in turn is a subset of the real numbers. Okay, yeah. I seem to have lost the connection there. Is that? Hello?
We can hear you.
You can hear me? No?
Yeah, we can.
Yeah, did it cut? It seemed to cut out for a moment. My screen went blank and all of you disappeared. You're still there?
Yeah, we are there.
Great. Okay. Great. Excellent. Okay. And the notation I'm using, is that clear? The way I'm what I've written here. Sorry, I have to go back now to my where is it? Sorry, I've got too many things on my screen. So everybody understands what this means here. Yeah, these are subsets. Okay, great, excellent. Okay, Again, I apologize if I'm saying things that are really easy. It's just because I don't know what everybody knows yet. So we'll start easy, okay? And so don't be offended if I say things that are obvious. I'm just checking in. It's better that way around than for me to say things that nobody understands. Okay, so we like to think of this as living on a line, right? So we have a line that we draw. It's an infinite line, goes on forever. There's 0, 1, 2, 3, 4, and so on this way. -1, -2, -3, and so on in that direction, okay? And so I've written in here just the integers, right? But of course we have other numbers living on this line. We have, say, the rational numbers like 1/2, or say in here, so this is -3/2, for example, and so on. So we've got rational numbers. And also we've got numbers which are not rational, it turns out, which live on this line. So things get quite interesting when you deal with, say, numbers that are not rational. So for example, there's a number in here, the square root of 2, okay? And the square root of 2 is, so if we make a square, this is a square 1, 1, 1, 1. This is a square. And the square root of 2 is that distance there. So that distance there from the one corner to the other corner. But that number, it turns out, cannot be written as a fraction. It's not in here. So the square root of 2 is not inside of Q. So it's a so-called irrational number. So we have numbers which are real numbers. You can write them as a decimal. So the square root of 2 is approximately 1.414 ... It goes on forever. Ad infinitum. So this goes on forever, but it's not a decimal. So this is not equal to A over B, where A and B are integers. You can't write it as a fraction like that. Okay, so that's important. So we've lots of these numbers. Another example of one of these numbers is in here. It's called pi. You all know pi. Okay, and so on. So there are lots of these numbers which are real numbers but not rational. And so we like to think of this as a continuous line, just a big long line going on forever. And we can add numbers on the line, and we know what that means. We sort of imagine adding numbers, adding 1 + 4 as moving up in steps along the line. We can also multiply numbers on the line. So I want to focus on the multiplication for a minute. So multiplication. What does it mean to multiply numbers on this line? So I'm going to redraw the line here for a second, because I want to think of this geometrically. So there's my 0. Let's say there's 1, there's 2, there's 3, there's 4, -1, -2. And let's just take, I'm going to denote by a little arrow here. This is the number 1. Now, what happens when I multiply by something? So let's say I multiply everything by 3. So what happens now? Well, my number 1 now gets moved up to the number 3. Okay, the number 2 here, it gets moved up to 6, and so on. So if I multiply by 3, so I have x, any particular number here, x, gets moved to 3 times x. And you can imagine the effect that has on the whole line, right? So the line now, what was my 1, now gets shifted up to 3. What was, say, 2 here, sorry, wrong color, here's 2, it now gets shifted all the way up to 6. A number like, say, -1, it goes all the way to -3. And so you can see multiplication by 3, what does it do? It expands the line, okay? So it expands the line times 3. Everything stretches. Does that make sense? Okay, so you can think of that geometric. Notice, by the way, 0 stays where it is. No, sorry, here. 0 stays put. Okay, doesn't get moved, but everything else gets stretched. What happens if we multiply by -1? Okay, so we have the line There's 1. If I multiply by -1, we now get this. The line, this goes the other way. Okay. If we take a number like 2, it goes to -2, and so on. So if we multiply by -1, we have the effect of reflecting the line through 0. 0 here, 0 here. Does that make sense? Everyone happy with that? Right. And so you can think geometrically, you can think of the multiplication of numbers as sort of moving the line around in various ways. Okay. Okay. So just a few observations. So basic observations about multiplication. Okay. So I have A, comma B. These are real numbers. Okay. Let's take another one, C. So I notice that if I multiply A times B, and I multiply that number by C, it's the same as if I multiply A times the numbers B and C. And this is called associativity. Have any of you heard that term before? Okay, so everyone understands that it doesn't matter. When I multiply, I have to multiply 2 things, but it doesn't matter which of the 2 I choose to multiply first. I get the same thing. Second, there's a number 1. And if I multiply my real number by 1, it doesn't change anything. This is called identity. And by the way, it's the same if I multiply on this side. Which leads me to another interesting point. If I multiply A times B, it's the same as if I multiply B times A. This is called commutativity. Okay, so far everyone happy? Has everybody heard all of these terms before? Yeah. Okay. So again, I'm sorry if it's all stuff you know, but there's no harm in us going through this. Now, here's a very important point. One of the things we can do here is we can do division. So if I have A and B belong to R and B is not 0, this makes sense. Well, what is it? What do we mean by A divided by B? What is this? What is this number? We also sort of all know, but we'd like to write this in a careful way. Well, it turns out that for every A in R, A not 0, we have a number which I'll call 1 over A. So that A times 1 over A equals 1. So this is called inverse. By the way, sometimes people write 1 over A as A to the power of -1. Okay. And so using that, we can make sense of the expression A over B. So A divided by B equals A times 1 over B, the inverse of B, or A B inverse if you prefer. That's what that means. So that's what we mean. That's how we make sense of that expression. Okay. So why did I mention all of this? Well, I first of all wanted to be clear on these words. I want us to know what these words mean because we're going to use them a little bit later, all of these words. So we want to understand the language. But if I go back up a little bit, sorry. Funny thing about this picture is it keeps getting bigger and smaller as I move it around. And if you go back, we have this geometric description of multiplication, of moving the line around, okay? Reflecting the line across at the 0 or stretching it or shrinking it. And now we have these algebraic notions, okay, as well. And this will be very important for my next question. So here's the question. What about 2-dimensional space? So what do I mean by 2-dimensional space? This is R2. If you prefer, we write it like this, R multiplied by R. This symbol here is a type of multiplication for sets. set multiplication, also known as Cartesian product. And all I mean here is the set of all pairs A comma B, such that each of A and B are real numbers. And let's draw a picture. Okay, so we have a picture here. I'll make that a bit smaller. So this is the same picture that we described at the very beginning with the X and Y axes. Okay, and we think of the first component here as living on the horizontal line. And we think of the second component here as living on a vertical line. And so we think of a point in two-dimensional space like that. Okay, you've all seen this kind of thing before. Everyone happy, right? Now, here's the question. I want to be able to multiply these two-dimensional numbers. Okay, these are points in two-dimensional space. So we want multiplication so A comma B times C comma D. So suppose I have some other number here, C comma D, equals what? Okay, we want to be able to multiply these numbers. Okay, and we would like the multiplication to be a nice multiplication. We want this multiplication to be, you remember the words I used above? Associative. We would like it to have an identity, some kind of 1. We would like it to have satisfy this inverse rule. And this is for, it'll turn out we won't care about the case when AB is 0, 0 for this inverse rule, just the non-zero ones. Okay. And also, if possible, commutative, although that may not be the most important one to worry about. Commutative. Does that make sense? And finally, geometrically meaningful. Okay, we would like there to be some geometric kind of explanation or reason behind the multiplication, in a similar way to the way the multiplication on the real line could be interpreted with a picture, right? That you could stretch or shrink things or flip things over. Okay, so that's the problem. Does everyone understand the problem? I'm going to stop for a second. I'll please ask me a question if you have. I'd love to have a question. Any questions from anyone? Any comments at this stage? No questions? Okay.
Mark, I had one there.
Yeah.
To mention the addition in the plane, the vector addition.
Oh yeah. Good point. Okay, let me quickly do that, and then I'll get back. I'm going to be coming back to all this in a minute, but yeah, that's a good idea. So let me just go back and I'll mention that. It's difficult to keep moving around the technology here, so let me. Yeah, so I'm focusing here on multiplication, but just as it was mentioned, I should talk about addition. Let me take. So let's take a pair of. I'll move over here for a second to answer John's question. So addition. So here we are in our two-dimensional plane, and let's consider a pair of numbers. So I'm going to denote these by arrows. So these are sometimes called vectors. I don't know if you're familiar with the term vectors or not. Have people heard the term vector before?
Yep. We've taken
Yeah,
it.
you have, great. Okay, great. So so we think of these as a pair of vectors. Sorry, I have to go back. I'm flipping between the two things. So vectors. So this is the first one. Let's say this is A comma B, and then we have another vector. Let's say C comma D, and of course we can add these things. So we can add A comma B plus C comma D, and you add it in the obvious way where you have A plus C. So you add this term with this term, and you add these two terms, and you get B plus D. Okay, and that's how you add these things. But there's a nice picture, of course, which is when you add them, you pick up the copy of the first vector and you move it forward. You pick up the copy of the second vector, you move it sideways, and you end up getting a point up here. And this is my new vector here, A plus C comma B plus D. And of course, as you may already know, you get a nice shape here, which is a parallelogram. So this is the parallelogram law or parallelogram rule for adding vectors. Okay, does that make sense? Okay, so this is how the addition works. Okay, so let me just go back down to this question for a minute. So I introduced two problems. One was this algebraic problem where you have equations you want to solve, and when you try to solve these equations, you get these square roots of negative numbers that appear. And the other problem is this geometric problem about multiplication of two-dimensional vectors in two-dimensional space. We want to have a way of multiplying vectors by each other to get a new vector, and we want that the new vector is somehow geometrically meaningful. So before I go further, do people understand both of those questions? Yeah? Everyone understands those questions? Yeah? Okay. Let me ask just a question that we'll come back to later. What about R3? This is three-dimensional space. So if I take three-dimensional space, I now have X, Y, and Z axes. And I consider a vector here, which is some A, B, C, and some other vector here, which is some D, E, F. Is there a sensible way of multiplying these vectors that's geometrically meaningful and which satisfies these nice conditions, right? Remember the conditions we want: associative, identity. I spelled identity wrong there. Sorry, let me fix that. Identity, inverses, and so on. Okay, can I find a multiplication which is nice, which has those properties? So let me just pose that as a question. Can you find a multiplication in three-dimensional space which satisfies the associativity condition, identity, inverse, etc. Or any of them, maybe not all of them, maybe just some of them, question mark. So I'll let you think about that question. I'm not going to answer that question right now. I'll let you think about that question. Okay, and if you want, you can even think about higher dimensional space, four-dimensional space, five, whatever other dimensions you want to think about. Okay, so I'll just pose that question for a minute before I go back to talk about the two problems. Okay, any thoughts on that three-dimensional question, by the way? Do any of you have any thoughts on that? What do people think? Can people still hear me? I'm hearing nothing.
Yeah, we can hear you.
You can hear me, yeah? What do you think, Lean? Do you have any thoughts on the three-dimensional question?
I'm not sure about it actually. I'm still thinking, but Abdullah shared something in the comment.
Oh, did he?
He
Okay,
said
let me have a look at the comments.
Yeah.
I forget to look in the comments. Hold on a minute now. Oh yes, there's a chat. Sorry. Yeah, that's it. So Abdullah, that's an excellent suggestion. Okay. Do you mind if I talk about Abdullah's question for a minute? Do people want to hear about? Yeah. So have people heard about the cross product? Have you all heard about the cross product?
Some of us.
Not really.
Some of you. Okay. So let me I don't want to spend too much time on this. I will tell you all about the cross product soon, but let me just give a quick answer to Abdullah's question, seeing as he asked it. So the answer, Abdullah, is I'm afraid the cross product doesn't work here, although it's a very good suggestion. So I'll just say note cross product is a very good suggestion, but it does not satisfy, and I'll just draw a little arrow here, these notions: associativity, identity, inverse. It doesn't satisfy these. Okay, so for people who don't know what the cross product is, don't worry about it today. I'll come back to it. I just wanted to throw this out there. But Abdullah, if you have a little think about the cross product and try to see, is it associative? Does it satisfy identity, inverse, and so on? You'll see that there are lots of situations where things go wrong. So it is a good multiplication, and it is geometrically very important, but it doesn't satisfy these nice conditions. Okay. Okay. Abdullah, does that answer your question? I'll look in the chat again. I keep forgetting to look in the chat. Yeah, great. Thanks, Abdullah. Okay, so as I said, it's a great suggestion, and I'll tell, for people who don't know what the cross product is, it's a really important geometric tool in mathematics, and I will maybe the next time we can have a little chat about the cross product. So let me go back to the original problem. Okay, the original two problems. Sorry, I have to. You're probably all laughing at me trying to use the computer. I'm not very good at this. So back to the first problem. Hold on. Back to problem 1. So as you can all see, in solving equations, we need, and I'll put here numbers, special kind of number, of the following type: a plus b times the square root of minus 1. Okay, we were seeing numbers that looks like this, where a and b here are both real numbers. Okay, so for example, if I take a number like 7 plus the square root of minus 100, you can see it turns out the way we're going to set this up, this will be the same as the number 7 plus the square root of 100 times the square root of minus 1. And of course, you all know that the square root of 100 is 10. So this is 7 plus 10 times the square root of minus 1. So these kinds of numbers were appearing in the solutions to the equation. So we have to deal with this. So the first thing we'll do to make things a little bit easier is adopt the following convention or notation. We will use I to indicate the square root of minus 1. And so we get that the square of I squared, is equal to exactly minus 1. Okay, so this is what we're going to use. From now on, the square root of minus 1 will just be called I. Okay, and we're going to define a collection of numbers. So these are the complex numbers. We'll call them C, with a funny little line, to be the set of all numbers a plus b times I. So the a and the b here are real numbers, and I squared equals minus 1. Okay, so this is what we're going to mean by the complex numbers. And you can see that it's a nice way to think about this is as a two-dimensional set of numbers, or two-dimensional space of numbers. And this is what this is all related to the two-dimensional problem I mentioned earlier. So we can think of every element in here is a pair of real numbers. So there's an A part and a B part. And the B is being scaled by this I here. And so we will consider all of the numbers that have the I scalar to be vertical and all of the other numbers that don't have the I scalar to be horizontal, like this. And so we get numbers that are formed with these two parts. This one here we'll call the real part, okay? And this one here we'll call the imaginary part. Okay. Does that make sense? Yeah? People
Yeah.
happy with that? All right, so this is, hello? Yeah. Great. And so you can think of this, we'll just put it next to our traditional, so this is called C. And then we have, of course, our old friend here, R2, two-dimensional space. And same thing, we have A and B, and we just have a number, we write A comma B. And so you can see that these two things are really two different ways of describing, in a sense, two different ways of describing the same thing. Okay, there's a correspondence between these two pictures. Okay, great. Okay, and so in a sense, when I start talking about C here, you can think of everything I do as having a kind of version over here for R2. Okay, and so in solving the problem for R2 of coming up with this nice multiplication for two-dimensional vectors, we're actually going to do it over here. Okay, great. So inside of C, we can add and we can multiply. Okay, so addition in C, we take complex numbers A plus B times I, and we can add it to another complex number C plus D times I, and we do it in the obvious way where we get this is going to be A plus C, that's the real part, plus B plus D times I, that's the imaginary part. Okay, and so this corresponds to the addition on this side, AB plus C comma D equals, and this is A plus C comma B plus D. And so you can see the same kind of correspondence, this part with this and this part with this, okay? And now here's where we get the multiplication. So remember the rule is that I, when it's multiplied by itself, I squared gives you -1. And so now if we have A plus B times I, and we multiply by C plus D times I, we're going to get A times C plus B times CI plus A times DI plus B times DI squared. And when you tidy this up, you get AC. And remember the I squared term here is -1. So you end up getting AC minus B times D. So this term here comes over here. Plus, and then I'll take out the common I here, and so we end up getting plus BC plus AD times I. So this term here is coming from that. Okay, everyone see how that works? And so there's a corresponding multiplication in R2. You can think of multiplying vectors in R2. Sorry, A times B, C times D. And you can define the multiplication to be simply AC minus BD, comma, AD plus BC here. Okay, and you can see that you get a correspondence. Okay, I did something stupid, but anyway. Anyway, so you can see this correspondence between these two terms. Okay, so that's the multiplication that we want. Now, the question is that you're probably asking, well, is that truly the multiplication that I want? Does it satisfy the nice conditions? So this is a little exercise for you guys. Show complex multiplication is associative. I'll let you do that yourselves. What about so what about an identity? What do you think the identity is going to be here? Well, the answer is simply 1. If I multiply 1 by any complex number, a plus ib. So remember, 1 is the case when it's, you can think of 1 as 1 plus 0 times I. And this is going to be simply a plus ib. So you have this identity 1. Now, what about inverses? Suppose a plus ib is not 0. Okay. So what is 1 divided by a plus ib? Because I need to know what that is before I can talk about things like c plus id divided by a plus ib. What does division mean here? Okay. So I'm going to explain how to work that out in a second, but do you understand the question, the problem? Okay. We want to know what it means to have inverses. We want to know what it means to do division. Yeah. Okay. No questions. Nothing. Okay, I'll go back. I was just checking the chat. I have to keep checking the chat because I might miss something. So let me show you a little trick. Okay. So first of all, I need to give you a term. For each a plus bi, the complex numbers, it has a friend. So each one of these has a friend. There is another number, a minus bi, called the conjugate. And if you draw this on the picture, so here's a plus bi. You can see its friend lives down here, a minus bi. Okay. And watch what happens if you multiply these two. You get, this is a squared plus bai minus bai minus b times I squared. When you tidy this up, you find that these two terms cancel. This is, of course, minus 1. And so you end up getting just a squared plus b squared here. And this is real. Notice this is not, there's no imaginary part here. This is entirely real. In fact, if you look at the picture, and you think that this distance here is a, and this distance here is b, then what does this number here represent? Well, this distance here is actually the square root of a squared plus b squared, right? Yeah. And so we have this notion of distance to 0. And normally people give this a name. They call this absolute value or modulus. Okay, so they write it with these two lines. And so we get that the absolute value of this is equal to a plus bi times a minus bi square rooted. Okay. So a little piece of notation, if I take a number like this, which looks like a plus bi, I usually put a bar over it, and this is a minus bi. That's how I write this. So before, I've got one more thing to say, and then we'll stop. But does that make sense, that notion? Okay. So how does that help us with inverses, with division? Okay. So how does this help us? Well, here's the trick. Okay, here's the trick. If I take 1 over a plus bi, hopefully you'll all agree. I'm assuming here that a plus bi is not 0, otherwise this doesn't make sense. And I write it as 1 over a plus bi, and I multiply this by a minus bi divided by a minus bi. First of all, does everyone agree those two things are the same, right? That this side is the same as this side, yeah? But if I write it that way, this equals a minus bi on the top times a plus bi times a minus bi underneath. And that equals a minus bi divided by a squared plus b squared. And that's a real number. Okay, that's a real number. So that's equal to a over a squared plus b squared minus b divided by a squared plus b, plus b squared times I. Okay, and that's how you work out the inverse. So every single non-zero complex number here has an inverse. Let's do one quick example, and then we'll maybe take a little break. So example, let's say 1 over 1 plus I. So what's this? So this equals 1 minus I over 1 plus I times 1